All right, this video is going to be talking about remainders in error bound. And so we're still talking about this in relationship to series and to Maclaurin and Taylor and stuff that we've worked with before. We're just going a little bit deeper into the topic. All right, so first we have the definition of an error bound. And the error bound gives the largest possible error in an estimate. So we've been using these different series to approximate things. Like if I wanted to find sine of 2, I could either plug it in my calculator and get the exact answer, or if I didn't have that ability, I could look at the Maclaurin polynomial or the Taylor polynomial and take it out to a certain number of terms and plug in 2. But when I plug in 2, that answer is not perfectly accurate. So depending on how many terms I found, or if I did something centered at 0, or if I did something centered at 1.9, or something centered at 1, it would make a difference to how accurate my answer was. And so what we're going to be calculating now is not just those approximations that we were finding, but then we're going to calculate the error, which is how far off our answer could possibly be. Okay? So there are two types of error bound that we're going to use. One is the alternating series error bound, which we're going to do first. That's these first couple of examples. And then the Lagrant error bound is the rest of what we're going to do, and that's where we're going to spend most of our time. All right, so if a series is alternating and decreasing, like the ones that we've been looking at, then the error bound is found by taking the absolute value of the next term. So if the last term that you used to calculate your approximation was the 5th term, then the 6th term would be how far off your answer could be. So we say the formula is the amount of error is less than or equal to the next term. So I don't know what I was meaning when I wrote this because it's missing a lot of words. So I think I meant find the error bound of the series. After using the first 5 terms to approximate, I'm not sure. So if we're using the first 5 terms to approximate f of x, then the first term would be plugging in 1. So if I plug in 1, I get positive 1 over 1, which is 1. If I plug in the second term, to get the second term, that'd be 1/2. Plug in 3 to get the third term, plug in 4 to get the fourth term, plug in 5 to get the 5th term. And so I would say that my approximation for f of x is about 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, 0.783. All right, and then if I wanted to see how far off my answer could possibly be, I would calculate the error bound. So I would say that error is less than or equal to the 6th term, but it's the absolute value of the 6th term. So I know that the 6th term would have been negative 1/6. The absolute value of that is positive 1/6, and so that's how far off this decimal could be. So 1/6 below that decimal. So it could have been, the actual answer could have been as low as 0.617, or it could be 0.783 plus 1/6. The highest the answer could be would be 0.950. Okay, so the actual answer for the function would have been somewhere in between there. If we have more terms, then our answer is going to be off by less. So if we had 99 terms, then the error bound would be 1/100th, because that's what the 100th term would be. And so that would be off by 0.01. And so that would mean our answer was more accurate, was a little bit closer to what it should be. All right, so given this, how many terms are required to get the error approximation to be less than 0.00005? Okay, so we're going to say that our error is less than or equal to 0.00005. And so what I'm going to do is I'm going to take this and I'm going to set the n plus 1 term equal to this, because that's how I found my error, is not the nth term, not what they gave me, but it's the n plus 1 term. So I'm going to say 0.00005 equals 1 over n plus 1 to the 6th. The reason I used positive 1 and not the alternating part of this is because this would have been an absolute value, so it doesn't matter if that's negative or positive, it would have ended up being positive when you did the calculation. So I'm going to go ahead and multiply this over here, n plus 1 to the 6th times the decimal, and then I can go ahead and divide the decimal over there. So I have n plus 1 to the 6th equals 1 divided by that decimal is 20,000. And then I'll take a 6th root, and I get n plus 1 is approximately 5.210. And I can subtract the 1 over, and n is approximately 4.210. So we know that our terms have to be whole numbers. We can't have a portion of a number. If I had 4.210 exactly, then that would have been this exact amount of error. So if I want to have less than that, then I need to be more accurate. So more accurate would be rounding this up. And so we're going to say that we need 5 terms to have even more accuracy. If we rounded down, then we would have less accuracy because we'd have less terms. So 5 terms is how many we would need, and that would mean that to calculate the error, you would use the 6th term. And so that's why our n plus 1 was equal to 5.210, is because the 6th term would have calculated that. 0.00005. All right, so that's how you do alternating series. You just look for the next term, and that tells you if you need to figure out how many terms, then n plus 1 is going to get you there. Okay, so that part makes a lot of sense. It's pretty straightforward. Next, we're going to look at Lagrange error bound, and that's where we're going to spend the majority of our time. So if you look here, you can see that we have this part right here, which we are used to seeing. This right here is the Taylor approximation. Okay, so that's pretty normal for us to see. What is not normal for us is to see if I evaluate this at A exactly, it perfectly equals something with a Taylor approximation. That's kind of weird because we know that our approximations should not equal something because they're approximations. So what that means is this is the approximation. This represents how far off of the approximation we really are. So if this part right here is the first 5 terms, then this part right here is the 6th term all the way to the infinity term. It's all the rest of them added together, okay? So we call this right here the remainder. Or another way to think of it is this part is the approximation, this part is the error, or how far off of the approximation you are, and then this right here would represent the exact value evaluated at A. Okay, so the part that we are going to be focusing on throughout the rest of the notes and throughout this part of the unit is we want to figure out how to calculate that remainder. And the remainder has this formula. So if you look at this, this seems really similar to n plus 1, n plus 1. That looks like the next term, and that's because it basically is. Okay, so I'm going to say find the next term. It is not always that simple, but it sometimes is. So we'll see somewhere it is that simple. Okay. So on the next page of your notes, there's a nice little history lesson on how this came to be. And then there's a special note in here about one little part of this. And that's this funky part right here that is talking about the part of the formula where you take the derivative and you have the derivative evaluated at the value that you have the polynomial centered at. We're used to seeing this as like f to the n of c, but you'll notice it doesn't have a c in there. And so this is the part that makes these problems a little bit complicated. this part right here is what we're going to spend the majority of our explanation on, because I think the rest of the problems are going to be pretty simple. So we're going to go ahead and start off with this first example before we come back to this part, because the first example just tells you what to plug in right there. So we're going to go ahead and do example 3. So it says, let f be a function with 5 derivatives on the interval from 2 to 3, and assume that the 5th derivative evaluated at an x value, we'll talk about this part later, is less than 0.3. So they're telling you right now, plug in 0.3 for that right there. And that's nice. Some of the problems will do that. They'll tell you exactly what to plug in, okay? For all x in the interval 2, 3. The 4th degree Taylor polynomial for f at c equals 2 is used to estimate f of 3. Right? And now they're asking how accurate is the approximation. We do not have to be able to write out the Taylor polynomial to be able to figure out what f of 3 is to know about the approximation. All we have to have is the information they gave us, okay? So I'm gonna start with writing down my little formula. So I'm gonna say the error is less than or equal to the 5th derivative evaluated at some x value, and then that's going to be multiplied. If it was a Maclaurin, we would say x to the 5th. If it's a Taylor, we say x minus the c value for the center to the 5th. And this is a Taylor, and it was centered at c equals 2. So I'm going to say x minus 2 to the 5th divided by 5 factorial. So right now, we're pretty similar to those alternating series where we say, okay, 4th degree Taylor polynomial, let's go ahead and find the 5th term, and that's going to help us figure out the error. So I'm going to say the error is less than or equal to, and then I'm going to plug in all my values. So my 5th derivative evaluated at an x value is some number less than 0.3. And so I'll plug 0.3 in because that's as wrong as it could be. It could be closer than that, but that's like the biggest number away that it could be. And then here I'm going to take the x value that I'm using to evaluate, so I'm going to plug in 3. 3 minus 2 to the 5th over 5 factorial. And so that means that my error is less than or equal to, and if you type this into a calculator, let me check my notes, you get 0.0025. So once we have those numbers calculated, then typically what we do is we find an interval that the real answer could be on. So I'm going to say the real answer for 3 plugged into the actual curve is going to be somewhere in between what we calculated it to be, and they're just telling you when they took their 4th degree polynomial and plugged in 3, this is what they got. So it's going to be between 1.763 minus 0.0025 and 1.763 plus 0.0025. So the actual value of the curve evaluated at 3 is going to be somewhere between 1.7605 and 1.7655, somewhere in between those. All right, so if you turn to the next page of your notes, it's asking, could the actual curve evaluated at 3 equal the decimal 1.768, why or why not? And the answer is no. And that's because if you look, 1.768 is not on the interval. Okay, so I'm going to say it's not on the interval. And actually, let's be more specific. I'm just going to say it's not on 1.7605. Okay, and then could 1.761 be the actual value? And the answer to this is yes, because if you look, 1.761 is in between those. Okay. All right. So what we're going to do now is we're going to look at this problem right here, and we're going to think about it in terms of what this paragraph right here is saying. Okay. So I'm going to go ahead and read this to you, and then I'm going to kind of show you what we consider when we do problems where we have to calculate that value for ourselves. All right, so what this is saying is whenever we consider one of these problems, we're going to have an interval from A to C. A is the number that you are trying to evaluate the curve for. So that A is the value that you're approximating, okay? And C is the center, all right? And it's not necessarily A to C. I guess it could be C to A. It kind of depends on which number is bigger, which number is smaller. And the reason it doesn't really matter is just because of the way your approximations work. They don't always have to be to the right of the number. And so Z is a value somewhere in between there. So what they mean by this is if you're picturing a graph of your derivative, your nth derivative, so this could be your fifth derivative or your second derivative or whatever your n plus 1 term is, if you are looking at the graph of that derivative, then you want to figure out whichever x value has the highest y coordinate on that interval. So you would check the actual A that you're trying to plug in, you would check the C for the center, you would check all the numbers in between. You are looking for the one that has the highest value of the y coordinate or the highest value of the derivative, which is why they say the maximum value possible. And the reason that you're doing that is because we are erring on the side of caution. So we're saying, like, worst case scenario, that number could be that big. And the reason why we do that is because we're trying to come up with a conservative estimate. The n plus 1 factorial is never going to change. The number we're plugging in, minus C, that's not going to change. And so this is the only thing we have control over. So what we're doing is we're giving ourselves a little bit of a buffer. Okay, so sometimes they're going to give you that maximum value. Sometimes you have to picture the graph of the derivative in your head. And so this would be only in problems where you are capable of finding that derivative, where you have enough information to actually find it. And then you'll think about what's happening on that interval and pick the biggest value that you can, all right? And then what you do is you just take that value and you plug it in, all right? So this is still the idea of the next term. That's still what we're doing, but now we're going to come in and we're going to think about the graphs of the derivatives if we have the information to do that in the problem, okay? So what we're going to look at next is example 4, and I think this example might feel a little bit confusing for us, and if we need to cover it more in class, we definitely can, or we can look at another example that's similar, okay? So what I want you to do is not look at this as example and think, could I do this on my own right now? I want you to look at this example and say, yes, I followed along with that, okay? That's all you have to do is follow along and make sense of it. You don't have to think about doing it on your own just yet. All right. So we're going to think about the 5th degree Maclaurin polynomial for sine. So I know that sine is x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. And we're going to use that to approximate sine of 1. So that means that sine of 1 is 1 minus 1 over 3 factorial plus 1 over 5 factorial. And we're going to do 5 decimal places on this problem just because we're talking about accuracy. And so more decimals are a little bit more important this unit than they usually are. Okay, so this is what our approximation is. So now if we want to talk about the amount of error we could possibly have, I'm going to say that the error is less than or equal to, and we have 2 options for this problem because I know that if n is 5, then n plus 1 is 6. But I also know enough about sine to know that we don't typically have an exponent of 6. The next exponent that would be in the pattern is 7. So in this problem, you can actually do it with 6 or 7 and have a valid answer either way, like an answer that we would count as accurate and correct even though they're both a little bit different, okay? So I'm going to write 6 here just so that I'm still doing n plus 1. But I'm going to write that this could be the 7th term if we wanted to do that. So, or 7. All right. If you need to actually write it out as 7, that would be fine. Okay. So this part right here is going to be us looking at the 6th derivative. And we're going to look at the interval from 0 to 1. And the reason we're going to do that is because Maclaurin polynomials are centered at 0. And 1 is what I'm plugging into the, or is what I'm trying to evaluate. So that means I'm looking at the interval from 0 to 1, okay? So right here, to show that this is the work that I did, I'm just going to say that I'm taking the 6th derivative, and I am looking at this on 0, 1. And if you want to say that you're trying to find a max, this is not like perfect mathematical notation. I looked it up for half a second and then I decided I wasn't going to waste my time. So there is a special way of writing that, but we're just doing this for our notes, okay? So what we're going to do actually is I'm going to show you guys a picture of the 6th derivative so that we can actually figure out what this value would have been, okay? So off to the side, we're going to go ahead and say that f to the 6th of x is actually negative sine x. And then we can talk about it for the 7th derivative as well, because that was another option for doing this problem. So the 7th derivative is negative cos x. Okay, so if we look at the graph of the derivative, this is the graph of negative sine x. And I'm looking on the interval from 0 to 1. So let me grab a marker. So I'm looking on this interval right here, from here to here. And what I'm trying to do is I'm trying to find the biggest y value. And since this is in an absolute value sign, it doesn't matter if it's positive or negative. I'm just looking for the largest number. So on this interval, the largest number would be right here at negative sine of 1. Okay? So that means that that is the value that I'm going to plug in right there. Okay? So I'm going to say error less than or equal to sine of 1. I went ahead and I took out the negative sign because this is an absolute value problem. And now I've got times 1 to the 6th divided by 6 factorial. All right, so that means that the error is less than or equal to, if I plug this into my calculator, I get 0.00117, right? I'm going to go ahead and write the work off to the side if I was to have used the 7th, just so you guys can see another example of this part right here, okay? So if I was thinking about my 7th derivative, which would have been negative cos x, and I was looking from 0 to 1, my biggest y coordinate, so not negative, not positive, just the biggest number, would have been right here, because this decimal would be smaller than this number right here. And so that's actually a y coordinate of 1, or negative 1, but basically of 1. And so if I was going to go ahead and write down the error for this one, I would say that that would be cos of 0 multiplied by 1 to the 7th divided by 7 factorial. And again, it's an absolute value. It's technically negative cos. And I did not plug that into my calculator ahead of time. If I plug that in right now, then I get this decimal right here, which is a little bit less friendly because it's written in scientific notation. But if we think about this, I have to move my decimal 4 places to the left. So if I move it 1, and then I would have 3 zeros. So that'd be 0.1230 zeros, and then 19 would be 20. All right, so these are the 2 different errors that we could have had depending on which number we used. Both of these are mathematically valid because sine happens to be one that skips exponents, okay? So I'm going to say, I don't know how you want to notate that that is one that I'm not using for this example, but it could have been what we used, okay? So what we're going to do now is we're going to figure out the interval that sine 1 really has to be between. So sine of 1 has to be in between 0.84167 minus 0.00117 and 0.84167 plus 0.00117. All right, so this side is 0.84050. And this one is 0.84284. So could sine 1 equal 0.87? Absolutely not, because it's not on the interval. So I'm going to say no, it's not on, not negative point. All right. Write a fourth degree Maclaurin polynomial for e to the x. So we have e to the x is approximately 1 plus x squared over 2 factorial, x to the third over 3 factorial, x to the fourth over 4 factorial. And now use that to approximate the square root of e. The square root of e is the same thing as e to the 1/2. So I'm going to say square root of e, that's e to the 1/2. And that's going to be approximately 1 plus 1/2 plus 1/2 squared over 2 factorial, 1/2 to the third over 3 factorial, 1/2 to the fourth over 4 factorial. Okay? All right, use your polynomial to approximate this. That's what we did. Sorry, if I plug that in, I would get 1.64844. And then find the error bound for the maximum error when the x value is less than or equal to 0.5. So they're saying if I was to find, we're plugging in 0.5. Okay? And so I'm going to do the same thing to calculate my error as before. So I'm going to say this was the fourth term, so I'm thinking of my fifth derivative. I'm going to put a z there because I'm thinking of a z that I plugged in, right? A value somewhere between Maclaurin, so somewhere between 0 and 0.5 is what I'm thinking of, and that's technically what this means as well. Absolute value of x is less than or equal to 0.5 is really the interval from 0 to 0.5. So I'm going to say that's, and then x to the fifth over 5 factorial, right? So what I'm going to do is I'm going to think about the graph of the fifth derivative. We know that the fifth derivative of e to the x is e to the x. So what I have is I have a graph of e to the x, and I'm thinking about the interval from 0 to 1/2. And so 0 is right here, 1/2 is right here. I'm thinking about which one has the largest value for an output or for the y, and so that would definitely be up here at 1/2. All right, and so that means that that value is the one that I'm going to use in the problem. So this would be e to the 1/2. So I'm going to say it's e to the 1/2. And then the number that we're plugging in that we were approximating for is 1/2. Right, and when I plug this into my calculator, I get 0.00043. Okay, so if I'm making an interval, then I'm going to say the square root of e is somewhere between 1.64844 minus 0.00043 and 1.64844 plus 0.00043. So it's somewhere in between those, and those values are 1.64801, 1.64887. All right, here's our last example. We're almost done. So we're going to go ahead and write the third degree Taylor polynomial. So f of 2 is 6. 4 times x minus 2, because the center is 2, minus 7 times x minus 2 to the second over 2 factorial plus 8 times x minus 2 to the 3 over 3 factorial. So this is approximating f of x. F of 2.3 is what I get when I plug in 2.3. And when I plug that into my calculator, I get 6.921, and I didn't round that to 3 decimals, it really just spit out that number. Okay, so if I want to find the error bound, it says the fourth derivative satisfies this inequality. So what they're saying is they did the work for you of looking at the graph of the fourth derivative, and they looked at the graph from 2 to 2.3, and they found that the highest value there for y was 9. So that means the derivative is less than 9, okay? And so that's why they're saying for all x on the closed interval 2 to 2.3. Okay, so we're going to find the error, and it is, I'm going to say f to the fourth of z times x minus 2 to the fourth over 4 factorial, and then we can go ahead and start plugging all these numbers in. So they told us to plug in 9, and then we're plugging in 2.3 minus 2 and 4 factorial. So if you plug this in, you get that the error is less than 0.00304. And so that means if we want to set up the interval, that f of 2.3 is somewhere between 6.921 minus 0.00304 and 6.921 plus 0.00304. And so the actual value is between 6.91796 and 6.92404. So based on the information we found, could 2.3 be 6.992? Definitely not. Between 9.1 and 9.2, definitely not. So no, it's not on 6.91796, 6.92404.